So good morning to everyone. I welcome you all once again to my YouTube channel for the supports microprocessors and microcontrollers, a series of lectures on it. In this class, I'm going to discuss about pin configuration of 8086 microprocessor. We know that the microprocessor 8086 was available in 40-pin dual inline package DIP. By using these 40 pins or 40 signals or 40 lines, the processor 8086 can communicating with the external devices like memory elements or I/O devices. Basically, the 8086 signals we broadly divided into three groups. Those are common signals, minimum mode signals, and the maximum mode signals. So this is our 40-pin diagram of 8086 processor. See here, friends. So these are the signals only present in maximum mode operation, that is from pin number 24 to pin number 31. The same signal have a different functions in a minimum mode operation of 8086. Hold, HLDA, a write bar, memory/IO bar, data transmit/receive bar, data enable bar, address/enable, interrupt acknowledgement. All these 8 signals are present in minimum mode operation of 8086. At the same time, the same 8 signals have an alternate function like a request/grant signal 0 and 1, lock signal, status signals S2 bar, S1 bar, S0 bar, and then Q status signals QS0 and QS1. The remaining 32 signals are common for 8086 operation. These 32 signals function is can't changes based on the mode of operation of 8086. We know that our 8086 can operate in 2 different modes. One is a minimum mode and second one is a maximum mode. Based on a mode of operation, only the signals from pin number 24 to 31, these signals function was a changes based on mode of operation. No change in the rest of 32 signals. Now we are going to discuss these signals one after other. So let me start with common signals. The functionality of these common signals are not changed with respect to the mode of operation. Just now I told you that under this category we have a 32 signals. These 32 signals function was a fixed irrespective of the processor, either it operates in a minimum mode or it was operates in maximum mode. What those signals? In that category, my first signals are address and data signals. AD15 to AD0. See here, pin number 2 to pin number 16 and pin number 39. These are our 16 address and data lines. These signals are multiplexer lines. That means the one time incident, these signals are act as address lines. In some other time incident, the same signals may act as a data lines. That's why these are called multiplexer signals. So these signals AD15 to AD0 becoming as A15 to A0, that is a dedicated address lines in a first clock cycle T1 of every machine cycle. We know that 8086 can do different operations like memory read, memory write, IO read, IO write. If you want to do these operations, we are using a different signals. Those signals activation and deactivation is done with reference to clock signal. To do each and every operation, we need a group of complete clock cycles. Based on that operation, we are performing either in minimum mode or it is in maximum mode. Here we clearly told you that these are multiplexer address and data lines AD15 to AD0 becoming as a dedicated address lines A15 to A0 only in the first clock cycle of every machine cycle. The first clock cycle in the sense T1 duration. From T2 onwards, that is the remaining clock cycles of a machine cycle, the same multiplexer lines becoming as a data lines D15 to D0. In our 8086, we are not maintaining a dedicated address lines and dedicated data lines. We are maintaining a multiplexer lines. Because of that, the number of signals present in our processor should be reduced. If you are taking our dedicated lines, separate address lines, separate data lines, no doubt the number of pins present in your processor was increases, automatically the size of IC was increased. It occupied space on the PCB also increases. In order to overcome these difficulties, what we do is we are not maintaining a dedicated signals. Instead of that, we are maintaining multiplexer signals. Similarly, our second category of signals under common signals category, address and status signals. That is A19/S62, A16/S3. These signals are act as a dedicated address lines like a previous case. That is A19 to A16 in a T1 duration of every machine cycle. Here, interesting thing is, these are higher order 4 address lines. Their function is different based on your processor is interacting with the memory or it is interacting with the IO devices. Whenever your processor is interacting with the memory, that means for memory communication, these 4 lines are used to carry higher order 4 bits of memory location address. But whenever the processor was interacting with the IO devices, that should be IO communication, these 4 lines may carry a 0 or they simply operates in tri-state. Because in case of 8086, the IO devices are addressed by using IO mapped IO case. In that particular case, each and every IO device can be addressed with a 16-bit. To identify an IO device, we need a 16-bit address. Whatever the 16-bit address your processor can generate, that should be carried by our lower address 16 address line, say A15 to A0. So obviously there is no need of higher order 4 address lines, that is A19 to A16, so that these are either carries 0 or they are simply operates in a tri-state. Similar to previous case, from T2 onwards of every machine cycle, the same signals are becoming as a status signals S6 to S3. They are giving us status information. So what this status signals provides an information for us from T2 onwards for every machine cycle. In that prospect, the status signal S6 always carries logic 0. There is no dedicated function that should be allocated to status line S6. So it always carries a logic 0. But the status line S5 always gives the status of interrupt flag IF. That means if your interrupt flag becomes 1, the time your S5 carries logic 1, your interrupt flag equal to 0, then your status line S5 becomes logic 0. So that always this S5 gives a status of interrupt flag. And we left with the 2 more status signals, that is S4 and S3. Always these are 2 status signals gives the information regarding to the segment which is communicating with our processor. We know that our processor will support 1 megabyte of memory. That 1 megabyte of memory can be divided into 16 logical segments. Those 16 logical segments, again, we furtherly divided into 4 groups. Under each group, we have 4 segments. Those 4 groups are, one is a code segments group, second one is a data segments group, third is a stack segments group, and last is extra segment group. But any instant of time, our processor is able to communicating with one memory location. That memory location comes under which category? It comes under either it is in data segment, or it is in code segment, or it is in stack segment, or it is in extra segment. That information can be provided by these status signals S4 and S3. Once if you identify S4, S3 is equal to both are 0, 0, your processor was interacting with a memory location that should be present in extra segment. If it is 0, 1, your processor was interacting with a memory location, the location was present in stack segment. It is 1, 0, the location is belongs to code segment. 1, 1, the location is belongs to data segment. Like this, S4 and S3 provides the information regarding to the segment which is communicating with the processor. And the next signal is bus high enable BHE bar / status line S7. This signal is act as enable signal for auto memory bank or higher order memory bank, which is nothing but BHE bar. In T1 duration, that is every machine cycle have a number of T states in T1 duration. This signal is act as a BHE bar, which is simply act as enable signal for order memory bank or higher order memory bank. From T2 onwards, the same signal is act as status signal S7, and we are not allocating any fixed function to the status signal S7. It always carries logic 1. The combination of a BHE bar along with address line A0, which gives the information regarding to either we are accessing a single memory location information from the memory, or we are accessing two locations information from the memory. Because here address line A0 is act as enable signal for A1 memory bank or lower order memory bank. We know that our 8086 will support 1 MB of memory that can be divided or organized into two physically available memory banks. One is order memory bank and second one is A1 memory bank. Each memory bank size is equal to 512 kilobytes. In order to communicating with either even bank or an odd bank, those banks should be enabled. Your odd bank should be enabled by using BHE bar, and even bank should be enabled by using A0 signal. If you are observing this particular table, a BHE bar, A0 both are becomes 0, 0. We are going to communicating with the two memory locations. That is a whole word is received or transmitted to or from memory. That means at the time your data lines D15 to D0 both 16 data lines should be in active condition. Because each memory bank we are connecting 8 data lines. For odd memory bank we are collecting D15 to D8. For even memory bank we are connecting data lines D7 to D0. Whenever BHE bar and A0 signal both are 0, 0, a whole word is received or transmitted from the memory. That time all 16 data lines should be in active condition. The next case is BHE bar 0 and A0 is 1. BHE bar it indicates active low, so that your BHE bar value is equal to 0, so that odd memory bank is enabled. So byte was accessed from odd memory bank. That time D15 to D8 data lines are active. For next case 1, 0 case, your A0 signal is 0. So even memory bank was enabled. A byte was accessed from even memory bank. That time D7 to D0 data lines are active. Once both the signals are 1, 1, none of the bank is active. It is a passive case or invalid case. And later we have interrupt related signals. One is NMI, means non-maskable interrupt. By using this particular signal or a particular pin or a particular line, the processor 8086 receives only non-maskable interrupt from an IO device. That means our processor always receives a type 2 interrupt from an IO device. What is a type 2 interrupt? We know that the type 2 interrupt is non-maskable interrupt. We know that for 8086, basically a non-maskable interrupt is nothing but a power failure problems. Those can be received by your processor by using a signal called NMI. And the next one is INTR. INTR full form is interrupt request. By using this signal, your processor can receive maskable interrupts from IO device. And we know that our 8086 will support total 256 interrupts. Out of that, one is non-maskable interrupts and remaining 255 are maskable interrupts. Those are 255 types of interrupts your processor can receive from an IO device and by using a signal called INTR, means interrupt request. And coming to the next signal is a clock, CLK. By using this signal, your processor can receive a clock signal from external clock generator. Because your 8086 didn't have inbuilt clock generator. It always depends on external clock generator for clock. We know that our 8086 can operate a minimum frequency of 5 megahertz and maximum frequency is nothing but 10 megahertz. So what are the frequencies that we required for 8086 operation? It collected that clock signal from external clock generator. Here that IC number is 8284. And thereafter power supply signals, VCC and ground. For our 8086, there are 3 signals comes under this. We have 1 VCC and 2 grounds. For proper operation of 8086, we require plus 5 volts power supply that we are connected at VCC. And basically VCC we can consider as a power entering point of our circuit, and GND, that means the ground, we consider as power leaving point from our circuit. And the next one is a reset signal. It is another important signal in our 8086. This is basically a bidirectional signal. If this signal received by the processor stops the current executing task, whatever the program that it was executing, it stop it, and it shift execution to an initial address that is a 4F0H. From 4F0H onwards, we have initialization program of 8086 was present. Once it receives this reset signal, what it do is, once again, your processor should be reinitialized. Reset in the sense reinitialize. That means once you turn on your 8086, what are the initial conditions we identified? The same initial conditions again, if you want to need one more time, simply we reset our processor. That time again, we are identify the initial conditions without switch off and again switch on our processor. So here what happens the first thing? It stop the current executing task and it shift execution to initial address that is 4F0H. The second thing is all its internal registers are loaded with their initial values. I'm not saying here that was a 0 because all our registers may not be loaded with a 0. And some registers loaded with non-zero values, especially our port segment register CS is loaded with a 4FH. But majority of registers are loaded with initial values that is 0. So that's why here what I was mentioned is all internal registers of 8086 are loaded with their initial values. And third thing was all internal buses are operates in tri-state. Because your processor has to initialize itself. It has to prepare itself to go and do the tasks which are assigned by the user in near future. To do those operations in a proper way, it has to prepare itself. That's why all its internal buses are operates in a tri-state. So this is what happened if the processor receives this reset signal. Similarly, if your processor want to reset any connected device, that means your processor want any device operation from beginning, simply your processor reset that particular device by sending a reset signal. And coming to the next signal is ready. So this is another useful signal. Basically, this signal can be used by slowly operated peripherals. We know that the speed of operation of process is far, far greater than the speed of operation of rest of the devices. If the processor identifies logic 0 on this, simply the processor is enters to wait state. That means it can't do anything. It simply sit idle. It will go on continuously monitors the status of this ready signal. As long as the logic present on this ready signal is equal to 0, our processor simply enters into wait state. It simply sits in wait state. Otherwise, the device who issues this ready signal to processor, that the device is ready to communicating with the processor. That's why here I said that this signal can be used by slowly operated IO devices. This signal synchronize the speed of operation of some external device with the processor speed. That's why it is called a synchronizing signal also. And next important signal is MN/MX bar. MN indicates minimum, MX indicates maximum. This is a signal which decides the mode of operation of our processor. If this signal is connected to VCC, no doubt our processor is operates in a minimum mode, which is also called a single processor mode. Otherwise, the processor is operates in a maximum mode. It is also called a multiprocessor mode. That means the signal is connected to ground or logic 0. This is very, very important signal, friends. Everyone has to remember its pin number is pin number 33. The next signal is a test bar. Basically, the signal examined by wait instruction. So with the help of wait instruction only, we can examine this test bar signal. What is the speciality of this? If the logic level on this particular signal or a pin is equal to 0, the processor operation is normal. There is no issue about it. Once we identify logic level on this particular signal is equal to 1, simply the processor is entered to wait state. How long it stays in wait state? Again, if we have to change logic level on this test bar from 1 to 0. And one more signal here is a read bar. That is basically a control signal. It is an active low signal. The control signal in the sense, if this control signal is active, This signal was generated by the processor. Whenever the processor want to perform a read operation on either selected memory location or an IO device, it will generate this control signal. So these are the common signals of 8086. The next coming to the second category of signals, that is minimum mode signals. These signals only comes onto the picture only when the processor is operates in minimum mode. That is our signal 33, which is MN/MX bar is connected to VCC. That is a pin number 24 to 31. This 8 signal function is somewhat different in this mode of operation. In that the first two signals, one is a hold and HLDA. Basically, these two signals are used for direct memory access operation in our systems. That's why these two signals we can call as the DMA related signals. The processor can receive the DMA request signal from a DMA controller through hold signal to gain control over the system bus by your DMA controller. For that, your DMA controller send a request signal to processor. And your processor can give highest priority to hold request than any other interrupts. It immediately responds to this request and it issues a grant signal to our DMA controller by using HLDA. HLDA means hold acknowledgement. This hold and HLDA both are do direct memory access operation between an IO device and a memory with the help of a DMA controller. While a DMA operation is going on in our system, our processor is logically disconnected from the system bus. The time your CPU can't sit idle, it can do data processing function by using its internal resources. The next one is a status signal M/IO bar. It is a status signal. This gives an information to us. The logic level present on the signal indicates the processor doing current operation is related to memory or an IO. If the signal logic level is 1, the current going on operation in our system is related to memory. Otherwise, it is related to IO. So it is a status signal. And next one is a control signal, write bar signal. That is a write bar signal. Again, it is a control signal. Like our common signal read bar. If the signal is active, the processor is want to perform a write operation on memory or an IO device. And next signal is the data enable, DEN bar. This is the basically signal is act as enable signal for bidirectional buffers. Once the signal is active, then whatever the information that should be present on data lines, that is a D15 to D0 is valid information. So this is the information regarding to our data enable signal. And the next one is the data transmit/receive bar signal, DT/R bar. This is a signal which is act as a data direction signal for bidirectional buffers. Your data bus is connected to these bidirectional buffers. For enabling of these bidirectional buffers, we are using DEN bar. For defining the direction of a data flow, we are using DT/R bar. If the signal logic level is equal to 0, the processor receives the data from memory or an IO device through bidirectional buffers. Otherwise, your processor transfers the data to other side. That is, the data is transferred to memory or an IO device by using a data lines. And the next one is ALE, means address/enable. This signal is act as enable signal for address/. And this is the signal is very useful for us to demultiplex or multiplex address and data lines and multiplex address and status lines. If the signal is logic level is 1, that is, if the signal is active, your multiplexed buses are simply act as an address lines. Otherwise, your multiplexed buses are act as a data lines as well as status lines. Coming to the last one, that is interrupt acknowledgement signal, INTA. By using this signal, the processor sends its acceptance information to interrupting devices. If the processor is ready to provide the services for the interrupts which it receives through INTR signal. So this is about minimum mode signals. Next, maximum mode signals. Again, the signals pin number 24 to 31. Their function is a little bit different what we discussed in a minimum mode. In case of this maximum mode, their function is completely different. Your processor can operate in a maximum mode only when this pin number 33 MN/MX bar is connected to ground. In that, the signals which we are using for our operation is the first category is request slash grant signal. That is RQ bar slash GT not bar and RQ bar slash GT1 bar. These are two signals are helpful for us to do DMA operation is in maximum mode. Here there is a possibility that your processor may receive these are two request signals from two different devices at a time. Then your processor can't provide a service for these are two requests. That time it should follow a priority. In that case, RQ bar slash ZT not bar have a highest priority than other, that is RQ bar slash ZT1 bar. The next one is a lock bar signal. This output pin indicates that other system bus master will be prevented from gaining the systems. That means in a maximum mode, your system may contains more than one processor, but we have only one bus. If any processor can use a system bus, then automatically it will generate a lock bar signal that indicates to the other processors present in the system is no one try to access the system bus because it was executing some important tasks. Basically, the signal is activated by the processor only when it was going to execute an instruction which should have a lock prefix. This lock bar signal is active as long as the processor execute an instruction which should have a lock prefix. Once that instruction execution is complete, automatically lock bar signal is deactivated. So that is the use of this lock bar. Next one is status signals, S0, S1, S2. All these are active low signals, status bar signals. These are active low signals. So by using these status signals, we are doing 8 different tasks. 000 case, that is interrupt acknowledgement, sending of interrupt acknowledgement. 001, we are doing IO read. 010, we are doing IO write. 011, we are doing simply halt. 100 opcode fetching. 101 memory read. 110 memory write. Coming to 111, it is considered as a passive because here the signals are active low. The combination present on these three signals is 111. That indicates that none of the status signal is active. That's why here the operation is passive. And coming to the last two signals, which are present in the maximum mode, that is QS0 and QS1. Basically, QS indicates Q status. These are two signals gives the status of instruction prefetch Q. It was a present in bus interfacing unit BAU of our 8086. So two signals, obviously we are getting four combinations. These are active high signals. The first combination is 00. That means no status signal is active. So that is a passive case or invalid case. It is 01. Then first byte of opcode we are accessing from instruction prefetch Q. It is 10. Your Q is empty. It is 11. Accessing of subsequent bytes was happened from the Q. So like this, the Q signals are useful for us. So thank you. So this is about the pin configuration of 8086. Thank you for watching. So we'll meet in next class.